Welcome to Math World. This video is about vector representation of a complex number and how to find the modulus of a complex number. The real numbers are represented by the points on the real line and the complex numbers are represented by the points on the Euclidean plane. To each complex number, there is associated point in the plane with coordinates given by an ordered pair x, y, where x and y are real numbers. We can associate any non-zero complex number, say z equal to x plus iy, with the directed line segment or a vector from the origin to the point x, y that represents z in complex plane. In fact, we call that Euclidean plane. This is real axis and this is imaginary axis. Okay, and any point, say this is z, okay, I can represent it as a vector directed from origin to point z. Okay, this usually written like this. Okay, this is a vector x plus I y. Now suppose I want to have a complex number. I want to represent a complex number z equal to minus 2 plus I in Argand diagram. That's like this. This is real axis and this is imaginary axis. Now the real value is minus 2. Okay, so this is 0, minus 1, this is minus 2. Okay, then minus 2 plus I into 1, that is I, right? 1. So imaginary axis, the value of I is 1. And if suppose I have minus 2 plus 2i, then I need to write over here. Okay, now this is minus 2 and 1. X value is minus 2 and y value is 1. So this is the point minus 2 comma 1 and this is the vector representing the complex number minus 2 plus I. This is the minus 2 plus I. This is the complex number representing, this is a vector representing a complex number minus 2 plus I. Okay, now suppose we want to add two complex numbers. Say z1 is x1 plus iy1 and z2 is x2 plus iy2. Then I want to add them and I want to represent them in Euclidean plane or complex plane. So how do we add two complex numbers? We add the real parts together, right? That I have explained in my last videos. So x1 plus x2 I into y1 plus y2. Okay, now I want to represent this in my complex plane. Okay, for that, say real axis and the imaginary axis. Now z1, say suppose z1 is over here. This is z1, complex number z1, and say this is z2, complex number z2. This point is x2 comma y2 and this point is x1 comma y1. Okay, now I want to draw z1 plus z2. Okay, thus x1 coordinate is added with the x2, so that will become coordinate of z1 plus z2, right? So this will be extended now. So say let us take somewhere here. I'm getting z1 plus z2. Okay, this is x1 plus x2 comma y1 plus y2. Okay, because these two should be added. Coordinates of z1 and z2 is added together to get the complex number z1 plus z2. Now suppose you want to subtract, say, z1 minus z2. In that case, say this is real axis and this is imaginary axis, and I have z1 over here, okay, and I have z2 over here. I want to draw z1 minus z2. Okay, when z2 is in this direction, when I say minus z2, then see, minus z2 means its x coordinate is also negative and y coordinate is also negative, right? So it's minus x2 minus y2, so that it comes down like this. Okay, this will be minus z2 now. This is now minus z2. I want to find z1 minus z2. z1 minus z2. So this comes like this. This gives me z1 minus z2. Okay. Now this vector representation of a complex number is helpful in finding the absolute value of a complex number. What does it mean? Absolute value means modulus of a complex number. Okay. Say if I have a complex number, non-zero complex number x z equal to x plus iy, then modulus of a complex number is a non-negative real number, that is a square root of x square plus y square, which is denoted by mod z. Mod z equal to root of x square plus y square. X is a real part and y is the imaginary part of a complex number. This is nothing but the modulus of a complex number. If you think geometrically, mod z is the distance between the point x comma y and between the points x comma y and the origin. Say this and this, say this is complex number z, right? Mod z means I'm taking square root of sum of the squares of the real part and the imaginary part, right? If you say, what does it mean? Means distance of this from this to this, right? This is the origin, so 0 comma 0. Distance between these two points is nothing but mod z. You can observe that you can use the distance formula. It's root of x2 minus x1 whole square plus y2 minus y1 whole square, right? X minus 0 whole square plus y minus 0 whole square, which is nothing but root of x square plus y square. So that's what I'm trying to say. Mod z is nothing but the distance between the point x comma y and the origin. So when we have y equal to 0, if suppose y is equal to 0, then it reduces to the usual absolute value. When y is 0, absolute value of z is nothing but x only, right? It's on the real number system. If I have two complex numbers z1 and z2, and if I say mod z1 is less than mod z2, then it just implies that point Z1 is closer to origin than point Z2. See, uh, this is Z1, suppose complex number Z1 or a vector Z1, and this is Z2. When I say mod Z1 is less than mod Z2, it means that distance between Z1 and origin is less compared to this. Therefore, I can say that the point Z1 is closer to origin than Z2. And as an example, suppose I have Z equal to minus 3 plus 4i. If I want to find out modulus of z, it's nothing but root of x square plus y square. X value is minus 3 over here. So minus 3 square plus 4 square, which is nothing but root of 9 plus 16. So it's 25, which is equal to 5. So modulus of z equal to 5. Now suppose z1 is x1 plus iy1 and z2 is x2 plus iy2, and I want to find modulus of z1 minus z2. Okay, this gives the distance between z1 and z2. I have explained. See, when z1 is like this and z2 is like this, z1 minus z2 is this, right? That gives me modulus of this vector, gives me the distance between these 2 points z1 and z2. So mod z1 minus z2 gives the distance between z1 and z2. How is it actually? Mod z1 minus z2 is nothing but root of x1 minus x2 whole square plus y1 minus y2 whole square. So this is z1 minus 2 z2. This point is x1 y1 and this point is minus x2 minus y2. Okay, so this distance is nothing but root of x1 minus x2 plus y1 minus y2, x1 minus x2 whole square plus y1 minus y2 whole square. And one more thing we can observe, when I have a complex number, say z, this is the complex number z, then this complex number corresponding to the points lying on the circle, okay, whose center is at origin, and say this is the complex number and this distance I can call it as say r, and this is the origin, say z0. Okay, so the complex number z corresponding to the points lying on the circle with the center at z0 and the radius is r, which satisfies the equation mod z minus z0 is nothing but the radius, right? So when I say thus corresponding to the points lying on the circle, it rotates depending on the real values and imaginary values. It rotates and it forms a circle, and that the radius of that circle is z minus z0. So suppose the equation is given to us, say z minus 1 plus 3i is equal to 2. Modulus of this equal to 2. This equation in fact represents a circle. Okay, it represents a circle whose radius is 2, no doubt in that, okay, with radius 2, and where is the center? Z minus Z naught, right? So center is Z naught, which is 1 minus 3. Z minus Z naught, so 1 minus 3. So sometimes they'll give you such equations, they'll give you the equation and ask whether it forms a circle or which shape it forms. It may be a oval or depending on the equation. Okay, here I just gave Z, so it depends. So when this is the form, this is the key. If it's a circle, then it should satisfy this equation. So from this I can say this forms a circle with radius 2 and center is at 1 comma minus 3. Now one more point, when I have mod z equal to root of x square plus y square, I want to find the square of my modulus value, so it's mod z square. This will be, in fact, x square is nothing but real part of z whole square plus imaginary part of z whole square, right? And you can observe one more thing, this real part of z, real part of z is always less than or equal to modulus of real part of z, right? Because I have modulus means it's takes a positive value always, right? So this real part of z, if it's a positive value, then of course they are equal. If it is negative, then of course this will be less than the modulus of real part of z. And of course this will be either it will be equal to mod z or it will be less than mod z. Similarly, I can write imaginary part of z is less than or equal to modulus of imaginary part of z, and of course it will be less than or equal to mod z. Minus 2 minus 3i, suppose I have this. Now what's real part of z? It is minus 2. Its modulus is real part of z, its modulus is modulus of minus 2, which is 2. Similarly, imaginary part of z is minus 3 and its modulus value, absolute value, is 3. Then modulus of z is nothing but root of minus 2 whole square plus minus 3 whole square, right? So this will be root of 4 plus 9, which is nothing but root 13. Okay, now you check when I take real part of z, okay, and its absolute value and modulus of z, when I write it like this, of course this is less than this, which is nothing but modulus of real part of z, and of course this will be less than modulus of z. This is the case where I'm having real and imaginary values as negative. It may be positive also, okay? Suppose this is positive, then this is positive, this is 2 and this is 2, so that equality holds in this case, okay? It depends on the values of real and imaginary part. It may be positive or it may be negative. So from these two, we can move to triangle inequality of complex numbers. So when I have two complex numbers, z1 and z2, the upper bound for the modulus of z1 plus z2 is always z1 mod z1 plus mod z2. We can observe that, see, when I have this is z1 and this is z2. uh, z1 and z2. Where will be z1 plus z2? This will be somewhere here, right? This is z1 plus z2. When I take modulus of this value, either this will be equal to mod z1 plus mod z2, or this will be slight less than individual sum of mod z1 and z2. And also we can observe that when I have this is z1 and z2 are separate here. Okay, now when I have like this, suppose this is my z1, okay, and z2 is collinear to this. Say this is z2 now. This is z1 and this whole is z2. Okay, now where is z1 plus z2? This whole itself is z1 plus z2, right? In this case, what happens? Mod z1 plus mod z2 will be equal to mod z1 plus mod z2, right? Hope it is clear. Suppose 0, z1 and z2, okay, are collinear. In that case, mod z1 plus z2 will be equal to mod z1 plus mod z2. If they are not collinear, if they are different, then mod z1 plus z2 will be less than individual sums of mod z1 and z2. I can explain you with this with an example. Say suppose I have z1 as 1 plus I and say z2 as 2 plus 3i, suppose. Okay, when I do that, when I draw these two, say 1 plus I, 1, 2, 3, 1, 2, 3. Huh? This is real axis and this is imaginary axis in my Euclidean plane. Okay, z1, where is z1? 1 comma 1. This is z1, right? Now this is z1. z2 is 2 plus 3i. 2 plus 3i. 2 plus 3i. This is z2, right? So when I take z1 plus z2, this will be this. Okay, I'm not that good at drawing. Okay, so this will be z1 plus z2. But suppose I have z1 as 1 plus I and z2 as 2 plus 2i. In that case, this is real axis, this is imaginary axis. So 1 plus 1i will be here and 2 plus 2i will be just continuation of that, right? So this is z1 and this will be z2. When you take a modulus values, here mod z1 is root of 1 plus 1, so it's root 2, and modulus of z2 is root 2 square, that's 4, plus 9, so it's root 13. And z1 plus z2 will be 3 plus 4i, and its modulus mod z1 plus mod z2 will be root of 9 plus 16, so that will be 5. Okay, you can observe that mod z1 plus mod z2, where I should write, here only I'll write mod z1 plus z2, and I'll compare with root 2 and root 13, right? Of course, root 13 is just say root 16 is 4, root 16 is 4, root 9 is 3, so it's just more than 3, it's in between 3 and 4. I'm adding root 2, it is 1.414. Okay, it will be just more than this 2. So you can observe this root 13 is somewhere 3.60 5 I guess. Okay, and this root 2 is 1.414, that we know. So it will be just slight more than 5. Okay, a bit. So in this case it's of course less than this. Okay, if they are not collinear. Okay, so this was the observation. When they are collinear, mod z1 we have already calculated, it is root 2, and mod z2 is 4 plus 4, it is root 8, or you can say 2 root 2. And then mod z1 plus z2. Okay, that's first you calculate z1 plus z2, it is 3 plus 3I. So that's 9 plus 9, 18, root 18, or you now you can observe this mod z1 plus z2. Okay, and mod z1 plus mod z2, they are equal because this is 3 root 2, this is root 2 plus 2 root 2, so which is nothing but 3 root 2. That's what I'm saying. If they are collinear, okay, like this, then mod z1 plus z2 is equal to mod z1 plus mod z2. So from this triangle inequality, we can also observe that mod z1 plus z2 is greater than or equal to mod z1 minus mod z2. Okay, how it is possible? Let us say this. Okay, say mod z1, I can write it as mod of z1 plus z2 minus z2, right? I'm just adding and subtracting. Now I'll just rearrange this as this, z1 plus z2 plus minus z2. Okay, now say mod z1 is equal to this. Of course, mod z1 is less than or equal to modulus of individual values, right? I can write this from the previous term. Mod z1 plus z2 is less than or equal to mod z1 plus mod z2, right? So from this I can directly write individual sum. Okay, this whole thing is mod z1. No, this itself is less than this, less than or equal to this. Now I take up this to this side, mod z1, this was positive. Okay, mod z2, because negative value of z2 is same as modulus value of negative number is same as its positive value, right? So this will be less than or equal to mod z1 plus z2. Same as writing mod z1 plus z2, reverse the sign, greater than or equal to mod z1 minus mod z2. This is okay, but I want to have this modulus of modulus z1 minus modulus z2, right? So take this as it is. So this will be positive. This is of course positive. This is positive, and this will be positive only when mod z1 is greater than mod z2, right? So this situation will be true. This is a positive value, right? This always gives me a positive. This is positive always. But this will be positive if mod z1 is greater than mod z2. Okay, that is the case, then only this will be positive. Now suppose if it's negative, what happens? If when this will be negative, when mod z1 is less than mod z2, right? When mod z1 is less than mod z2, we just have to interchange the complex numbers z1 and z2. Okay. I'll do it. Complex numbers z1 and z2. So it was mod z1 plus mod z2. This was the expression greater than or equal to z1 minus z2. I want the result to be positive here. So if this is not the case, if this is the case, then I'll just interchange z1 with z2 and z2 with z1. So that's same as writing mod z2 minus mod z1. And this is same as writing mod z1 plus z2 will be greater than or equal to minus of, suppose I can even write it like this, mod z1 minus mod z2. Is it okay? See, if this is the case, if z1 is mod z1 is less than mod z2, then I have to write it like this. That is same as writing negative of this. So there are two options, one either the negative value or the positive value, right? So that means it's a modulus value. Therefore every time this is less only, right hand side is less only. So I can directly write mod z1 plus z2 is greater than or equal to modulus of mod z1 minus mod z2. This is the important result we use in many of the problems. And of course this is not only true for positive sign over here, this is even true for the negative of z2. For that I'll write, in fact I can write mod z1 plus or minus z2. I'm just writing the upper bound for that, even for the negative. Okay, mod z1 plus mod z2. This is the upper bound. Either you add or subtract. When you take a modulus, this will be the upper bound, and the lower bound mod z1 minus mod z2, its modulus. This is the lower bound. Okay, it's just because this happens even for negative value. It's just because I know minus z2, modulus of minus z2 is same as z2. Just because of this, upper bound and lower bound are true even if you subtract complex numbers and then you take a modulus. So when I do this, the equation 1 was like this, right? Mod z1 plus mod z2 is less than or equal to modulus of z1 plus mod z2. Okay, this was the expression, first statement. Okay, this one, upper bound. So when I replace z2 by minus z2, okay, for this I'm proving, for this negative case, I'm just replacing z2 with negative z2, right? When I do that, this will be mod z1 and this will be mod of minus z2. But minus of minus z2 and its modulus is same as mod z2 only. So this will remain as it is. Okay. So this is even true when you replace z2 by minus z2. And for the lower bound, expression is like this: z1 plus z2 is greater than or equal to modulus of z1 minus modulus of z2. Right? This is the expression. When I replace z1 by z2, z1 minus z2, this will be modulus of mod z1 minus mod z2. Minus z2 means when I take modulus, its value won't change. This will remain as it is. Okay, so this won't change. Therefore, this is true. This is the same upper bound even if you add complex numbers or if you subtract the complex number, and this is the lower bound. So from all this together, I can directly write the lower bound first mod z1 minus mod z2. This will be the lower bound for the modulus of complex number z1 plus or minus z2, and the upper bound is mod z1 plus mod z2. Okay, I'm sorry, this is the mod value. So this is the final expression you need to remember to solve many of the complex numbers, and it's very helpful in deriving many complex analysis problems. Thank you.